We will continue with fun and interesting applications of electromagnetic induction. Let's start by thinking about this situation. We've talked about it a little bit already. But if we have a magnet and we move it down toward a loop of wire, and I'm just going to draw my loop of wire as a cross section. So we've got a magnet moving down toward a loop of wire. What's going to happen as that magnet moves down toward the loop of wire? The magnet fills the space ahead of it with a magnetic field. And as it gets closer and closer to that loop of wire, more and more of those field lines are penetrating the loop of wire. So the flux is increasing, but it's toward the bottom of the page. So a current gets set up in my loop of wire out of the page on this side and into the page on the other side. The current gets set up to oppose this change. It wants to create its own magnetic field pointing up toward the top of the page. That means I could redraw this. I could have my magnet coming down, and instead of a loop of wire, that loop of wire acts like a little electromagnet. And what direction is it oriented? With a north pole up. So what happens here? They repel, or the falling magnet, the magnet that's moving down, its motion is slowed down by its interaction with the loop. Now let's allow our magnet to continue to fall. So we had this situation, right? We had a magnet, we had a loop of wire, and the magnet was coming down toward the loop of wire, and we saw what happened. Now we're going to allow that magnet to pass completely through the loop of wire and continue to fall down below the loop of wire like this. So now our loop of wire is above the falling magnet. What does the magnetic field look like from this magnet? It points toward the South Pole. And as the magnet moves farther and farther away, the field is getting weaker and weaker. So a current is set up in that loop of wire to try to add to the field. That means my falling magnet looks like that, same as it does in the real situation. And my loop of wire actually behaves like a little electromagnet. But this time, the north end is down. It has switched polarity. And what do I get here? An attractive force. What does that do? It slows the falling magnet. In both cases, the motion of the magnet was hindered or reduced by its interaction with the loop. As it falls down toward the loop, a repulsive force slows it down and prevents it from falling too fast. And after it goes through the loop, it's attracted, which slows it down and prevents it from falling too fast. Eddy, E-D-D-Y, is the same term that's used in streams when these small currents form on the edges of streams that are flowing water. So the eddy currents are small electrical currents that form in our conductors due to the interaction with the magnetic field. So let's take a look. Let's turn the situation sideways here. We'll have a magnetic field coming perpendicular to the page. So we have a magnetic field confined to this region of my page. And I'm going to move a conductor into this region of space. I'll make it a pendulum. So if I let go of this pendulum and allow it to swing down into this region of magnetic field, what happens is we have it coming from a region with no magnetic field into a region with a magnetic field. And the magnetic field is pointing into the page. So the flux in this part of our conductor is increasing into the page. A conductive material, it's a solid conductor, but it acts no different than a loop of wire does. We have an increasing flux. A current is going to get set up to try to oppose that change. So we're going to get a current that's set up in this direction. Now we have a current moving toward the top of our page for the most part, right here in this section. And that current is in a magnetic field. It's going to feel a force. What direction is the force on that current? To the left. Remember, the current on the other side is outside of the magnetic field region, so it doesn't feel a force. Only the current that's in the region with the magnetic field feels this force. That force slows down the moving conductor. And it doesn't matter whether it's moving into the magnetic field or out, just like we saw with the dropping magnet earlier. Didn't matter if it was moving toward the loop of wire or away from it. Its motion was hindered either way. The same is true here. If I make my pendulum swing out the other side, where this pendulum is swinging in this direction, the magnetic flux is getting reduced as the conductor moves out of the magnetic field region. So a current is going to get set up to try to increase it. We have a current moving in a magnetic field. What direction is the force? To the left, slowing down our moving conductor. It doesn't matter whether it's moving into the region of magnetism or out of the magnetic field region. The force slows it down either way. And these currents, these small loops of current that are forming here, one over here, those are called eddy currents.